Hello everyone and welcome back to another lecture. We are in chapter 10, Analytic Geometry. This is a relatively short chapter. It's only 4 sections we're going to cover. Section 10.1 is just description of conic sections or simply conics. And really sections 2, 3, 4 is all we got to do. We're going to discuss those conic sections. So let's begin with Section 10.1. Now, conic sections, the study of conic sections dates back to almost 2,000 years ago. So actually with Apollonius of Perga. Apollonius of Perga. Now Perga, from what I understand, is like the old city in Turkey. So you can do more research on that and see exactly where Perga is. It no longer exists as Perga. They've renamed it since then, but nonetheless, the man whose a statue you're looking at, which looks like me after sleepless nights grading exams, that's the gentleman who actually created. He's the cause of all this interesting stuff that we learn about and work with and apply to current situations. So Apollonius of Perga, around 2 BC, he's the man that actually discovered conic sections. He had 8-volume textbooks on conic sections. Now imagine an idea, somebody's idea who's been around for over 2,000 years, because we are now 2020, this is 2 BC, so it's over 2,200 years. The mathematics that he has developed still works, so that must be very notable and respectful for what he has done. So I have some things about Apollonius here. Actually, these are some of these. I'm not sure if all of them or some of them are just copy-paste job from Wikipedia to just kind of show you what's out there about him, which is not all of it, but it's just a little bit about Apollonius. His textbooks have been translated to many languages, so what you're looking at, which I'm sure nobody can understand here, this is the translation into Arabic language. So his books have been translated to many languages. I think, if I'm not mistaken, to at least 5 or 6 different languages. And of course, they have named a moon after him, Apollonius. So, very important figure, a towering figure in mathematics. And of course, Leibniz, which is one of the founders next to Newton of calculus, quotes, "He who understood or understands he who understands Archimedes and Apollonius will admire less the achievements of the foremost men of later times." So anyway, very interesting subject. So what is this about? Well, the conic sections, when we talk about conic sections, we're talking about the intersection of a flat surface, a plane, which is what this blue surface is, a plane, with the naps of the cone, what we call the double napped cone. Now the double napped cone, by the way, here on the left, I'm looking at this figure, is actually generated through what we call the generator, which is simply a line. That's what this is. See that generator? It actually generates the cone itself. So if that's the center of that generator, and of course this is a line, so theoretically this thing goes indefinitely in both directions. Okay, but if you look at this line segment here, and suppose this is the axis of rotation of the generator, and imagine revolving this generator either clockwise or counterclockwise, doesn't matter. If the top portion rotates in a counterclockwise direction, the bottom portion rotates in a clockwise rotation, correct? And you can try it. Just grab a ruler and try to do this. And this is the direction that the bottom portion from the center will revolve. Now, as a result of this rotation, we're going to get a cone up here, which is the upper nap, and we get another cone down here, right, which makes up the lower nap of what's known as a double napped cone. Okay, double napped cone. All right, now again, depending on how a flat surface crosses the outside, remember the cone itself is hollow because as a result of the rotation of a generator, there's nothing inside the cone, it's hollow. So we get different impressions of the flat surface crossing this cone at various angles. If, for example, if the flat surface crosses this either the top or the bottom, the upper or the lower nap of the cone, parallel to the base of the cone, then the result will be a circle. If it crosses it at an angle here, and of course there's an angle of generator here, and you can relate the angle of the surface to the angle of generator and make it more elaborate. But for now, if the surface crosses the either upper or lower nap of the cone in such a way that it creates an ellipse like this, then of course that cross section is an elliptical cross section. Okay, the flat surface could cross the upper or the lower nap of the cone in a way that it generates or produces a parabola at various formations, the parabola. And finally, if the flat surface crosses both naps of a cone, and the resulting impression that it leaves on the cone would be a hyperbola. So that's how these conic sections are generated. In all, there's 4 of them. We have circle, ellipse, parabola, and the hyperbola. Now, for each of these, if the plane contains the vertex of the cone, remember this is the vertex of the cone. So if the plane contains it, for instance, in the case of the circle, so here's my plane, and it contains a vertex. Now you can see that this is really not a circle, it's a single point, isn't it? So if the plane contains the vertex of the cone, the intersection of the plane and the curve, and the cone, the plane and the cone is going to be a single point, or it could be a line in the case of a parabola, like here's a surface. There you go, and the surface right there, see it contains the vertex. So the parabola actually, we say, degenerates to a single line. So each of these conic sections, all 4 of them, have their own what we call degenerate cases. A circle starts out big, the radius shrinks, and it degenerates to a single point. The ellipse could be this large, and then eventually notice how it's shrinking, and ultimately the ellipse is also going to degenerate to a single point. The parabola degenerates to a line right in here, right? That would be the line. And the hyperbola degenerates to 2 crossing lines like that. Okay, those are all degenerate cases, just so you know. Our work in this chapter is we would like to study the equation of these conic sections. And remember again, by the conic section, we're talking about the impression the surface leaves outside of the double nap cone, either the upper, lower, or both naps of the cone. Okay. And we're not going to do much with and hardly anything at all with the degenerate cases. Okay. And now the circle, and remember, circle is a special case of an ellipse, right? So our focus is going to be primarily in the sections that we're going to cover. It's going to be on the parabola, ellipse, and the hyperbola. Now, as far as the usefulness of this, well, conic sections are actually used in modeling many applications, real-world application, folks. For example, we can use parabolas in describing searchlights. They're used in design of telescopes, lenses, things like that. Ellipses are modeled for orbits of planets. In fact, if you look at Kepler's law of planetary motions, that tells us all planets revolve around the sun in an elliptical path. So ellipses are very useful as well. They're also used in design of what we call whispering galleries. I don't know if you heard of that or not, but whispering galleries is a really interesting concept. I'll tell you more about it when we get to the section on ellipse. And hyperbolas, for example, are used to locate lightning strikes and model nuclear cooling towers. Okay, so very, very useful topic that we're going to address. Again, all we're going to do in sections 2, 3, and 4, the next 3 lectures, is that we're going to simply talk about these 3 conic sections: parabola, ellipse, and hyperbola. Okay, so that's all about this section. Again, nothing, no examples, nothing. Everything we do will follow in the feature sections. Okay, thank you for watching. Again, very brief video. It is just on the idea of conic sections. So we'll start with parabola in the next lecture. Thank you for watching.